Hello and welcome to our today's webinar about the application of cloud-based CFD for external aerodynamics projects. First of all, I would like to introduce myself. My name is Milad. I'm the product marketing manager here at SimScale. And as a part of my role as a product marketing manager, I'm organizing and conducting several workshops and webinars across the year about different topics which are related to simulations. And before I joined SimScale, I worked also in motorsports as a CFD engineer and as a consultant, and therefore I've gained some experience about the application of engineering simulation and flow simulation for aerodynamics development, which I would like to share with you today. Yeah, now let's take a look at our today's agenda. So at the first 5 to 10 minutes of this webinar, I will quickly introduce you to simulation and engineering simulation in general. So we will discuss in like 2 or 3 minutes what are the general benefits of using simulation. And after that, I would also like to introduce you to SimScale, which is the world's first cloud-based platform. And today you will actually have a kind of a sneak preview regarding one of our latest features or one of our latest solvers, which enables you to perform CFD simulations without any need for meshing. And yes, later we will talk about this, and I will show you an example, and we will explain like what are the advantages of using meshless methods for aerodynamic development. At the end, we also have time for your questions and answers. So if there's anything you're curious about, you want to learn more about, just write a message into the question box, and I will try to answer your questions on the fly or latest during the Q&A. Yeah, let's start with the general benefits of simulation. And well, if you ask this 10 people about, they will give you 10 different answers. So there are a lot of different perspectives on this topic, simulation, engineering simulation. But since our today's topic, our today's webinar is dealing with aerodynamics, let's try to understand why CFD, so why fluid flow dynamic simulation can help to improve your engineering process. Well, whenever it comes to external aerodynamics, we are talking about an application where we expecting to have significant high loads. And when I, for example, was working in motorsports, our aim was to generate as much downforce as possible and to reduce the drag as much as possible. For those of you who are not very familiar with race cars or motorsports in general, so the idea of a race car is that if you have additional downforce, that you can drive faster through corners and therefore gain an advantage in these corners and set a faster lap time. However, back to our example, and in the end of the day, it's a very special application, but somehow it's also very similar to, let's say, every problem you are maybe dealing with, which is involving external aerodynamics. And for example, in F1, the idea is to improve the car from race to race. And usually the process is that you design, let's say, you want to improve something, for example, to increase the downforce on the front axis of your car. And what you usually do, you start to redesign the existing solution. And in the past, for this, wind tunnels were used. That was the only way to somehow predict the flow around an object. And this means you need to design the full part, not only the surface, but only the inner structures. You need to manufacture it. And only this process can take up to 4 to 6 weeks. And in general to that, CFD, also computational fluid dynamics, allows you to replace this wind tunnel test with virtual experiments using the computer. And they are much faster and cheaper and easier to perform than a wind tunnel test. And that's basically the main benefit of simulation. It allows us to design quicker and better. And in the end of the day, during a design process, it's a lot about learning. I mean, most of times things does not work as expected at the first time, and their CFD can be a crucial help. because it helps us to reduce our time investments, not only because it can prevent us from doing design mistakes but also because it's much quicker than wind tunnel testing. At the same time, it's cheaper, and also an aspect. In contrast to wind tunnel testing, CFD provides us with a much, let's say, a different kind of results. It's maybe not as accurate as a wind tunnel test, but we actually have insight to all the flow variables, so to the pressure and velocity for every point in the flow domain at every time step. And this gives us a huge insight about the flow structure, and that helps us not only to understand what is happening, but why it is happening. And from what I've told you, you must think, well, CFD seems to be a very interesting tool, and you may wonder if I tell you that less than 5% of the engineers in the world are using simulation, which means that they have direct or indirect access to those tools like CFD. And there are a lot of different reasons. And more than 6 years ago, when SimScale was founded, the idea or the vision of the founders was to make every engineer able to access simulation and to democratize the adoption of engineering simulation. And back then, there were 3 main barriers identified which are preventing a majority of engineers from using simulation. And well, in the end of the day, you can really summarize it to these 3 points. First of all, what we would call a kind of access or financial barrier. With traditional on-premise simulation tools, you have a significant upfront financial investment. We're talking about up to 30,000-40,000 of euros or dollars just for buying, the hardware. You need different kind of computers. You need strong servers for the computing. You need a powerful graphic workstation for post-processing. You need the licenses, which can be very expensive based on how much cores and how many different modules you want to use. So you end up in a very high initial investment, which is much too high for a lot of small companies, or especially if you just need simulation like for a dedicated project. On the other hand, even if you would have access to the hardware and software for free, it's not only about owning it, but you also need to set up everything, to maintain it, to update it, to install a license infrastructure. And usually for this, you really need a dedicated person who will just manage your simulation infrastructure, which adds additional costs and complexity, especially for small companies. And finally, which is, from my point, the most important point, what we call the know-how barrier. So 99% of traditional simulation tools are designed for simulation experts and not for those who are actually designing real products and want to leverage these tools. And that's why we came up with SimScale. SimScale is the world's first web and cloud-based simulation platform. So it not only allows you to perform a CFD simulation, but also supports several other disciplines like structural simulation or thermal simulation. And as I mentioned, SimScale is web and cloud-based, and this means that you don't need to buy any dedicated or any special hardware or any special software. The only thing you need to use SimScale is the standard web browser and the internet connection. On simscale.com, you can create your own free account within 5 minutes, and from then on, you can run very complex and sophisticated engineering simulations in your web browser. And I don't want to talk too much about our product and our platform, but let me just share some very interesting USPs of SimScale with you, and after that we will start to talk about aerodynamics. So as I mentioned, usually with on-premise software you need to buy different modules, and the license price is depending on how many different physical solvers you want to use, how many cores, and at SimScale you don't need to mess around with that because SimScale is an all-in-one tool. So independent from if you're using structural mechanics, if you want to use a structural mechanics module, if you want to do an aerodynamic simulation or a aerodynamic simulation, the same platform, the same user interface. No additional licenses or things you need to buy, or so it's really a multi-physics tool at your fingertips. And since it's cloud-based, it's super fast and easy to use, so you can use it with actually any device. We have customers running it on the Chromebooks or on the netbooks or tablets. I personally prefer to run it on my personal 6-year-old laptop, and it's still super fast, and that's thanks to cloud technology. So all the data is stored in the cloud, all the computations are performed in the cloud, and therefore you also don't need to install anything because everything is happening in the cloud. For sure, you can download at any time everything, so results and also data. And due to the cloud-based approach, we also have something which we call real-time support. And a lot of companies actually promise this, but at SimScale, this really becomes real, because inside the SimScale user interface, we have integrated chat, so you can directly reach out to our support and user success team. You can also reach them by phone or mail, and beside support, which is free for everyone by email, and chat and phone support for sure is free for our paying customers. We also offer consultancies, webinars, and training. And since I raised the topic, that's maybe the most awesome point about SimScale. SimScale is very cost efficient, and actually it's a free tool. Because you can start risk-free and without any upfront investment with our so-called community plan, which gives you exactly the same functionality like the professional plans. The only difference is that your public projects, that your prod simulation projects will be public, and that it only includes email and forum support. And it's therefore mainly used by students or NGOs or hobbyists. However, if you just want to explore, first of all, if simulation could be interesting for you, try our platform for free. And due to the cloud-based approach, we also have some enhanced collaboration functionalities. You can not only share projects with one mouse click with the support, but also with colleagues, customers, and clients. And SimScale is more than just a tool. It actually brings together people and content. So SimScale is also one of the largest engineering communities in the world, with more than 100,000 users from all around the world. And a question which is raised nearly every time I'm conducting a webinar is, what's about security and privacy? Well, that's an important point for us. So as I mentioned, there are public projects, and we have more than several thousands of them, and obviously they are private, so everybody can access them, including the geometry, the simulation results, and the meshes. On the other hand, if you have a commercial plan, all your projects are private, nobody else can access them without your permission, without that you are sharing them, even not the support team. And we use different encryption methods, including AES, to really encrypt your data at several points to really make sure that it's safe at all times. Yeah, finally, where is CFD or SimScale ever used? We actually have customers in, I would say, literally every industry, but majority of them come from AEC, and there we have a lot of engineers which are dealing with building aerodynamics. And yes, for sure, we also use a lot in terms of improving internal flows, like in the valve and pump or in the machinery industry. Well, and now let's talk about today's topic. And first of all, let's see if it seems like there was a question. Okay. Well, now let's start to talk about today's topic. And yeah, you are joined to learn about the application of CFD for external dynamics. And today we would like to share with you a project from one of our customers. So it's a little bit different geometry, but it's actually a real-world project. And this company is designing, manufacturing, and distributing cargo boxes for cars. And these roof boxes, I don't know how common they are around the world, but in Europe, especially in Germany, they are very common. Usually people use them when they drive with the car to ski. And they can impact the aerodynamics of a car. And this is a very important aspect for them, especially since they need to get certified and to prove that, for example, the device will not negatively influence aerodynamic of a car. And As a short introduction, just to understand for those of you who are dealing with external aerodynamics but with a different application, the great thing about CFD is that it allows us to get an insight about the real three-dimensional flow field around the car. And this allows us not only to calculate very quickly like which forces are acting or which moments are acting on the car, but it actually gives us information about the pressure and velocity for every point on the surface and every point around the car. And their CFD can be used, for example, not only to understand what is happening, in this case, what is the value of the drag coefficient, but to understand why. And for example, you can use it to identify high pressure regions which are creating or contributing to the drag force, or to investigate low pressure regions in the wake, which can also increase the drag. And another very important aspect, whenever it comes, especially when it comes to car, is stability and handling of the car. And if you think about it, such a cargo box, in the worst case, can add a lot of additional lift, which will make the car less stable, but at the same time, which is a much bigger problem usually, is that it can increase the sensitivity of aerodynamic sensitivity of the assembly of car and roof box. And with sensitivity, in this case, we mean that, just imagine if you have a slight side wind, for example, it can, or the wind direction is just a little bit changing. It can happen that suddenly the aerodynamic characteristics of the car are changing. And this can, yes, be quite problematic, especially if you're driving fast on a highway. And CFD allows us, therefore, to really understand what is the optimal design and to identify best configuration with the help of the post-processing. And now let's switch to our live demonstration and take a look on what we will do today. So, and this is maybe the most important point from technical reasons. The only thing you need to perform a fluid flow simulation or external flow simulation, however you want to call it, is you need a CAD model. And this model necessarily needs to be clean and closed. With this we mean that you need as I mentioned, a closed model, so a volume model if possible. That's the best thing. Where nowhere air can enter into the geometry, and it needs to be as clean as possible, which means you should usually reduce the amount of complexity, especially, for example, assemblies like the brakes or the suspension are usually simplified, since they are not adding a lot of impact on the overall flow, but resolving the small features takes a lot of time. However, so you need this CAD model, you usually upload it, and then comes a very important point. Most of the other tools, there is a process called meshing. And until some weeks at SimScale it was also necessary, and for a lot of applications still it's necessary that you mesh your model, which means you need to create a simulation model and to divide your fluid domain into small cells which are dictating the local accuracy of a simulation. And with SimScale lattice Boltzmann method solver, this is the path from now on, and you can directly simulate and create a simulation based on a CAD model. And once you've set up your simulation, you can visualize the results in the web browser and take your design decisions. Yeah, now let's take a look at today's objectives. So when it comes to the simulation or validation of aerodynamics of this cargo box, it's necessary to not only consider the cargo and roof box, but also the car. Therefore, we use a kind of generic car model. And we actually did 3 simulations. The first one was was containing the car only without any cargo box, which is a kind of reference. And then we have 2 different designs for the roof box. And now let's switch to the SimScale platform. Yeah. And as I mentioned, everything I'm doing here, it's happening in the web browser. So this is my project link, and only I can open this project with that link. And now I'm inside the simulation project, which was prepared by one of my colleagues from applications engineering. And this is actually the whole user interface of SimScale. So everything is happening inside this interface. There are no additional or changing windows. And one thing we need for every simulation is the geometry. And in this case, we have 3 geometries. We have the car assembly with the roof box design number 1. We have design number 2. And we have the car without the roof box. And this is a step model, so which can be exported by basically every CAD system, but you can not only upload step models or IGES or STL models, but also native CAD formats like SolidWorks or AutoCAD or whatever you are using. So, and the only work which need to be made was to to simplify, to seal like the wheels and the wheel openings, and yeah. And usually you need to mesh this, and this is the most time-consuming process of the whole simulation. And with SimScale's new innovative solver, which is based on a let's say mesh-free method, where the mesh is created automatically, that's the more correct description, you can directly create a simulation based on the CAD model. So let's just quickly take a look on how this is working. So first of all, you have to choose as a solver the incompressible lattice bolt span. Then you need to select which model you want to simulate, in our case a car without a roof box, and then you need to define some geometrical primitives. So first of all, your bounding box, and that's actually it. But in addition, we also added some so-called refinements to, like, where we can, but we don't need to care about the discretization. We just need to define the dimensions. Yes, and then we also created 3 so-called result slices. And the reason is that this lattice Boltzmann methods, here we are actually dealing with transient results, and that's another big advantage. So usually you do steady state, but as we all know, external aerodynamics are never steady state, they're transient always. But since it's this transient simulation always, for post-processing, we need to specify in advance which reasons we want to post-process. However, then you just need to define the boundary conditions, so the inlet, the outlet, the walls, and then you can start the simulation. And in this time, we simulated 5 seconds of real fall time, which should be enough for doing a series averaging. Yes, and once this is finished, we can take a look at the results, for example, at the force plots, but also at different result slices. It's super fast, and for example, if we know we can, for example, go on for example now create a cutting plane in y direction, and then then you can like visualize different things, for example, velocity in x direction. You can also export it if you want for do local post-processing. However, so, and just to introduce you, because we will work with some coefficients in the next 10 minutes. So the frontal area of the car, let me start the other way. Why do we use coefficients? A lot of people use, when they talk about aerodynamic forces, they talk about absolute values. And in some applications it might seems to be okay, but usually it's better to work with coefficients, because you maybe heard about the Reynolds number. So if you think about that idea that there are similarity effects, and if you think about the idea of scale wind tunnel testing, you usually want to have an idea about the meaning of results, which can be adapted also to other geometrical scales. And that's why I work with coefficients. So in this coefficients, the forces are related to the frontal area of our object, the free stream velocity, and the fluid properties, so the density actually. And yeah, and now let's start to take a look at the results. First of all, this is the transient velocity profile of the car without the roof box. And you can create this kind of animations on the platform or with downloading the results and using the free ParaView post-processing tool. And it's very interesting because just to avoid any confusion, not the slice is moving, but the time is changing. We have 5 seconds of real-world time. And here you can see that we have a kind of wake structure, like behind the car. And obviously some eddies are shaded here like. And initial, that's the important thing, our initial drag is, our drag coefficient is 0.0005, and its initial state we have a lot of lift. And if we now take a look at the pressure profile, it's obvious why, because at the roof of the car we have a massive low pressure area. And this low pressure area is like sucking up the whole car and creating a lot of lift. And now let's take a deeper look at the two roof box designs and how they will impact the flow around the car. So design number 1 has a streamlined front, and the back is straight. So this part here is straight. And actually there are two effects. First of all, the roof box itself will increase the frontal area of the car, and therefore the drag will usually increase. And the idea is that here is a streamlined front will give a smoother flow and reduce the additional drag as much as possible. And if we now take a look at the results, we can see that there is a large wake formed behind the whole car roof box assembly, and there's actually seems to be an interaction between the wake created by the roof box and the wake created by the back of the car, and therefore the drag value increased, but the lift decreased a little bit, since due to the high pressure region on the top of the roof box. If we now take a look at the pressure distribution, yeah, it's obvious that we still have, sorry, we don't for sure, we have not a high pressure but a high velocity region on the top of the car, and this one is creating a low pressure region. However, the lift seems to be smaller, since we also have flow separation and not the whole roof connect anymore as a kind of wing. And in contrast to that, the box number 2 is a little bit designed different. It has a tapered back, so we have a kind of small diffuser here. And it will still increase the frontal area of the car. And this sleek design will also still allow a smooth streamlined flow for the front. But due to the backward taper, we will reduce the size of separation vortices. And the idea is that if the flow remains attached, the increasing pressure will reduce the drag. And that's also what's happening. So the vortices are separated, and therefore we have a lower drag, and which is very important, a much lower lift also. And if we want to understand this, it seems like that the new formed wake now is disturbing the flow over the cargo box and therefore reducing the lifts there. Now let's take a look at the ISO volume showing the wake region for the car with and without the roof box. So in this case, this visualization is illustrating how the wake is formed behind the car. And here you can really see how the two vortices are joining. By the way, also an effect which is heavily utilized in motorsport, especially F1. And what is also very interesting, with this transient solver, you can also calculate pressure variations. And without a box, the pressure value remains actually very constant at each point, except the wake region for sure. That's something you want, because this is like giving you a hint about how the driving behavior of the car will be influenced by the varying pressure values on the surface. If we now have the cargo box, we have much more fluctuations on the whole back, on the whole roof of the car. Yes, and on this slide you can actually see a like short summation of what we discussed. So CFD can really help at different stages of aerodynamic design to optimize the designs, especially because it allows us to understand the flow behavior. And in this case, it's all about boundary layer separation. And this is something where you can use CFD, but should be cautioned whenever using simulation, and make sure that your assumptions are valid. And yeah, the second design, yes, helped to solve our problem. And if we now take a look at the summarized force lag, the initial design had a higher drag and a higher lift, and the improved design now has lower drag and lower lift. And actually, it will take a user around 3 hours of manual time to prepare, run, and analyze simulation results. And it needs 3 hours of computing time per simulation model, so overall 150 core hours were used for all configurations. And yes, in return, it helped to massively improve the design and also to gain design confidence. Thank you very much for your attention and being here with me. Now I would like to answer some of your questions. And let's start. So the first question is by Saj, and Saj wants to know, how do you calculate the drag force FD? Well, Serg, as I showed you, there is a result control item, which is where you can calculate the force acting on the car. And inside this result control item, you can also specify or define your frontal area, and then this be calculated automatically by SimScale, and you can easily download just a CSV file containing the results. Raul Corrales asked about the aspect of blockage ratio and percentage in the simulation. And if there are any recommendations from our side. Raul, that's a very good point you're raising, and that's really important. A simulation, CFD can stand for computational dynamics, but it can also stand for colorful desktop. And a lot of people are using like simulation as a marketing tool, and it can be used like this, but if you really want to have meaningful results, you need to invest some time and use the right setting and models. And this blockers ratio, Raul, means that your virtual wind tunnel box needs to have a decent size compared to the dimensions of your model. So, and 5 to 10% is a good assumption. It also depends on the application, but for external aerodynamics of a race car, 5 to 10% it sounds good. However, you should think you don't need a high resolution far away from the car or from your object. So usually does not cost you a lot to create a very big bounding box. And F1, they really have massive bounding box, just to really make sure that from a numerical point of view, the result is not impacted too much. Next question is by Shahid. Shahid wants to know, in the case if we do external aerodynamics analysis of the flow around the car, but the model is cut in half, how to use the coefficients there. Well, Shahid, it's also a valid question, but actually let's discuss it together with the slide. So in the case you have a half model, your force will also reduce by 50%. At the same time, your frontal area will reduce by 50%, so the coefficients will still stay the same. That's exactly the idea of the coefficient, because if you have the coefficients, you don't need to care if it's a full or a half-K model. It does not leave any room for interpretation. Praful and some other ones know which solver we're using. The solver is called PaceFitch. It's not an open source solver. It's a solver which was developed for us and also by us. And yeah, it's only available on the SimScale platform so far. Sergey has a last question. He wants to know, analyzing the flow behavior on a car, which are the most important parts to focus on? Well, Sergey, that's a good question depending on your role. Usually there are people working in NVH. They are interested only in some vortices, for example, which are created by the mirrors because you want to reduce the noise or the noise generation by the car. If you talk to an engine guy, he will say it's about improving the intake, the exhaust, and the engine burning chamber design. And if you talk to a dynamist or designer, he will say it's all about aerodynamics. Well. All right, I hope that I answered all your questions. Thank you very much for being here with us. It was a big pleasure. I wish you a very nice rest of the week, and we will send you the recording by email. Bye.